Students, today we will discuss about special functions, that is beta function and gamma function. The gamma function and beta functions belongs to the category of the special transcendental functions and are defined in terms of improper definite integrals. These functions are very useful in many areas like asymptotic series, Riemann zeta function, number theory, etc., and also have many applications in engineering and physics. The gamma function was first introduced by Swiss mathematician, that is Leonhard Euler, in 1707 to 1783. So now we see what is the definition of the gamma function. Let n be any positive number, then the definite integral 0 to infinity e power minus x power n minus 1 dx is called gamma function of n, which is denoted by gamma of n, and it is defined as gamma of n is equal to integral 0 to infinity e power minus x power n minus 1 dx, where n greater than 0. Okay, so this is the definition of the gamma function. Gamma of n is equal to 0 to infinity e power minus x into x power n minus 1 dx, n greater than 0. Now we have to see the properties of the gamma function. Gamma of n plus 1 is equal to n into gamma of n. Okay, now from this we can able to write the definition of gamma n also. Gamma n is equal to gamma of n plus 1 by n. Okay, we have two properties here. Gamma of n plus 1 is equal to n into gamma of n. Similarly, if you take n into the left hand side, then gamma of n is equal to gamma of n plus 1 by n. Okay, and the second property is gamma of n plus 1 is equal to n factorial, where n is a positive integer. Third one is gamma of n is equal to 2 into integral 0 to infinity e power minus x square x power 2n minus 1 dx. And one more one, gamma of n by t power n is equal to integral 0 to infinity e power minus tx into x power n minus 1 dx. One more property, gamma of 1 by 2 is equal to root pi. Okay, we will prove this one afterwards later. Gamma of 1 by 2 is equal to root pi. This is the very important essay question every year asking in the university exams. So we will prove afterwards. Gamma of 1 by 2 is equal to root pi. So these are the formulas about properties of the gamma function. Next, coming to the beta function. The beta function is denoted by beta of m comma n or b of m comma n. So it is defined as beta of m comma n is equal to integral 0 to 1 x power m minus 1 minus x power n minus 1 dx, where m greater than 0 and n greater than 0. Okay, beta of m comma n is equal to integral 0 to 1 x power m minus 1 minus x power n minus 1 dx. M and n are greater than 0. Now we will see some properties of beta functions. Beta of m comma n is equal to beta of n comma m. This is called symmetry of beta functions. Beta of m comma n is equal to beta of n comma n. So we will see proofs after this slide. We will see how can you prove this one, symmetry property of the beta function. Similarly, beta of m comma n is equal to 2 into integral 0 to pi by 2 sin power 2m minus 1 theta cos power 2n minus 1 theta into d theta. Beta of m comma n is equal to 2 into 0 to pi by 2 sin power 2m minus 1 theta cos power 2n minus theta dt. This one also will prove. Okay. Third one is beta of m comma n is equal to 0 to infinity x power m minus 1 by 1 plus x power m plus 1 dx. Okay. Similarly, beta of m comma n is equal to 0 to 1 and x power m minus 1 plus x power n minus 1 by 1 plus x power m plus 1 dx. These are the some properties of the beta function. Okay. Now we'll see the property here, symmetry of the beta function. So just now we see in the last slide First property, symmetry of the beta function. You can prove this symmetry property in easiest manner by using simply the definition of beta function. Okay, we know the definition of the beta function. Beta of m comma n is equal to integral 0 to 1 x power m minus 1 into 1 minus x power n minus 1 dx. This is the definition of the beta function. Now we have to show that beta of m comma n is equal to beta of n comma m. This is called symmetry of the beta function. So simply put 1 minus x is equal to y. So this implies that differentiating on both sides, dx is equal to minus dy. Okay, and here the limits also, when x is equal to 0, then y will become 1, and when x is equal to 1, the upper limit, if you put x is equal to 1 here, y is equal to 0. So therefore the x limits 0 to 1 will be 0 to 1 will be changed into the y limits 1 to 0. So therefore now we will rewrite the beta function as, so beta of m comma n is equal to, so 0 to 1 will be changed as 1 to 0. So therefore 1 to 0, in the place of x we have to write 1 minus, in the place of y we have to write 1 minus y. So therefore in the place of x we have to write 1 minus y. So 1 minus y whole power m minus 1, and 1 minus x as y only. So therefore y power n minus 1, and dx is equal to minus dy. Clear? So then y power n minus 1, 1 minus y power m minus 1 dy. So now clearly if you observe, this is again in the form of the definition only. Since you know that the integral form, integral a to b f of t dt, you can able to write integral a to b f of x dx as a variable function. So like in the place of y, simply you are writing as a x, because we are defining the definition in terms of x. So therefore simply in the place of y we are writing x by using this property. So x power n minus 1, 1 minus x power m minus 1 dx. So we know that this is in the place of m we have n, and in the place of n we have m. So therefore this is the definition for beta of n comma m. Okay, so therefore you can clearly prove that the symmetric property beta of m comma n is equal to beta of n comma m. Okay, hence we proved the symmetric property. And second property, beta of m comma n is equal to 2 into integral 0 to pi by 2 sine power 2m minus 1 theta cos power 2n minus 1 theta d theta. Okay, so beta of that one, second property. So this property also you can prove easily by using the basic definition of the beta function. You know that basic definition of the beta function is beta of m comma n is equal to integral 0 to 1 x power m minus 1, 1 minus x power n minus 1 dx. Put x is equal to sine square theta. We have to remember all this substitution. Then this property is very easy to prove. All the students has to remember this substitution in the exam. Simply we put x is equal to sine square theta. Okay, so by taking the differentiation on both sides, dx is equal to 2 sine theta d theta. This you can write as sine 2 theta d theta. Actually, if you take the differentiation on both sides, dx is equal to 2 sine theta, and with respect to sine theta is cos theta, and with respect to theta is d theta. 2 sine theta cos theta, that is sine 2 theta d theta. So now apply the substitution in the above integral, that is beta of m comma n is equal to left side, and the right hand side will becomes the limits. If you see the limits, when x is equal to 0, the theta will become 0, and when x is equal to 1, the theta is equal to pi by 2. This is pi by 2. Okay, so therefore 0 to, it cuts here, this is originally pi by 2. So this is 0 to pi by 2. In the place of x we have to put sine square. So sine square theta whole power m minus 1, and 1 minus x means 1 minus sine square theta whole power n minus 1 dx is equal to sine 2 theta d theta. Okay, simply we are substituting. Now see here, just I am writing here. So this is I am writing as a powers, this one 2m minus 2. Okay, expanding. So sine power 2m minus 2 theta, and 1 minus sine square theta is cos square theta. So therefore cos square theta means cos square of n minus 1 means, so cos square of 2n minus 1 2 theta, and again you know that the sine 2 theta d theta is nothing but 2 sine theta cos theta. As usual also you can write here, so 2 sine theta cos theta d theta. So here 1 sine theta is there, and sine power 2m minus 1. So here sine power 1, 2m minus 2 plus 1 means 2m minus 1 theta. Similarly cos power 2n minus 2, here cos power 1, 2n minus 1 theta d theta. So easily we can able to prove that beta of m comma n is equal to 2 into integral 0 to pi by 2 sine power 2m minus 1 theta cos power 2n minus 1 theta d theta. So this is the second property of the beta function. From this property, you can able to write one more property. You can able to prove one more property. In the examinations, they are asking anyway, either this property or if you take 2 into left hand side, that is 1 by 2 beta of m comma n. So in the examinations, they are asking like this. Show that or prove that integral 0 to pi by 2 sine power 2m minus 1 theta cos power 2n minus 1 theta d theta is equal to 1 by 2 into beta of m comma n. So same proof. At the last step, we have to write, we have to take that 2 into left side. So therefore, that is 1 by 2 into beta of m comma n. So therefore, this proof will have the two properties. Clear? And next one, third property also we can able to prove that. One more one. Beta of m comma n is equal to beta of m plus 1 comma n plus beta of m comma n plus 1. What is that? Beta of m comma n is equal to beta of m plus 1 comma n plus beta of m comma n plus 1. This one also we can prove easily by using the basic definition of beta function. All of you know that the basic definition of beta function is given by beta of m comma n is equal to integral 0 to 1 x power m minus 1 1 minus x power n minus 1 dx. Okay, now I am taking right hand side. Beta of m plus 1 comma n plus beta of m comma n plus 1. So first I am taking the property, that is a formula by the definition of first function, beta of m plus 1 comma n. So this is m, let us treat this is m, this is n. So integral 0 to 1 x power m minus 1. So in the place of we have m plus 1, so therefore m plus 1 minus 1 will become m only, and 1 minus x power n minus 1 dx. Similarly for the second function, integral 0 to 1 x power m minus 1 and 1 minus x power n minus 1 originally, and in the place of n we have n plus 1, so therefore n plus 1 minus 1 will become 1 minus x power n dx. This is dx, some x is cut here, this is dx differentiation. Now that is, the integral will be written as, here from these two integrations I am taking the function as common, x power m and 1 minus x power n minus 1. Okay, so here also we have the x power m minus 1, 1 minus x power n whole, and we have the dx. So commonly we can able to write, and from these two functions I am taking the common as x power m minus 1 from the second function and 1 minus x power n minus 1 from the first one. So if you take the common, in the first one we have x power m minus 1 into x will become x power n only, and 1 minus x power n minus 1. So 1 minus x into this one. When you multiply, the above step will be getting. So therefore we can able to take the common like this. X power m minus 1, 1 minus x power n minus 1 will take common. If you multiply with x, this will be the first integral, and if you multiply with the second one, 1 minus x, this one will be the second one. So x power n minus 1 will be the same as it is 1 minus x whole power n minus 1 into 1 minus x, that will be the 1 minus x whole power n. Here also x power m minus 1 into x means, sorry, here also x power m minus 1 into x will become x power m and 1 minus x power n minus 1. Okay, so therefore, and here we know that x plus 1 minus x, x will be cancelled, 1 will be how, that will be the, what is the remaining thing is x power m minus 1, 1 minus x power n minus 1 into dx, and you know that this is the definition of the beta function. So we'll have the left hand side. So if we take the, we are starting with the right hand side and we are proving left hand side. So what is here we are doing, simply we are taking the definition and we are applying the definition for beta of m plus 1 comma n and beta of m comma n plus 1. By using the basic definition only we are proving this one. And we can also like that, we are proceeding like this, we can able to prove some more properties. The last property is, if m comma n are positive integers, then we can able to prove that beta of m comma n is equal to m minus 1 factorial, n minus 1 factorial by m plus n minus 1 factorial. So I am giving this example problem for the student, for the student assignment. Okay, so all of you go through this basic definition. I am also giving hint here. The basic definition of the beta function is beta of m comma n is equal to integral 0 to 1 x power m minus 1, 1 minus x power n minus 1 dx. Here some cut, 1 minus x power n minus 1 into dx, and use the integration by parts here. By using the integration by parts, we will get this result. Okay, so this is the homework for the students. Okay. Next, now we will see some problems. So they are asking in the examination by using like this. So show that integral 0 to pi by 2 sine power m theta cos power n theta d theta is equal to 1 by 2 beta of m plus 1 by 2 comma n plus 1 by 2. So this is very easy to prove. So if you are starting with the left hand side, 0 to pi by 2 sine power m theta cos power n theta d theta is equal to just I am writing like this: 0 to pi by 2 sine power m minus 1 theta cos power n minus 1 theta, and I am multiplying with sine theta cos theta. So again, if you take the sine, multiply sine theta here, this will become sine power m theta. If you multiply the cos theta here, this will become cos power n theta d theta. Just simply I am writing here powers m minus 1 and multiplying with sine theta and cos theta. Now here I am taking square and m minus 1 by 2. This 2 and this square will be cancelled. Again it will be in the form of sine power m minus 1 theta, and similarly here also cos power n minus 1 theta sine theta cos theta d theta. Now here the substitution is very important. All the students have to remember this one in the examination. So take put sine square theta is equal to x. So take the differentiation on both sides. 2 sine theta cos theta d theta is equal to dx by is equal to dx. If you take 2 into this side, sin theta cos theta d theta is equal to dx by 2. So if we consider the limits, when theta is equal to 0, x will become 0. When theta is equal to pi by 2, that x is equal to 1. So therefore the limits will become 0 to pi by 2 will be as 0 to 1, and in the place of sine square theta we have to take x. So therefore x power m minus 1 by 2, and cos square theta is 1 minus sine square theta. So therefore 1 minus x power n minus 1 by 2 dx, because you know that sin theta cos theta d theta is equal to dx by 2. I am separating that 1 by 2 from the integration because that is a constant. So therefore from this step you have 1 by 2 into integral 0 to 1 x power, this power m minus 1 by 2 I am writing like this: m plus 1 by 2 minus 1. So if you take this one, if you multiply, minus 2. So m plus 1 minus 2 means again minus 1 only for our convenience. So we are writing like this. So m plus 1 by 2 of minus 1. So that will become, so this is minus 2. If you multiply, that is plus 1 minus 2 means minus 1 again. So here also n plus 1 by 2 minus 1. Similarly again it is also plus 1 minus 2 will become n minus 1 by 2. So what is that? If you see, this is in the form of x power, if you let us consider this is m, x power m minus 1, 1 minus x power n minus 1, basic definition of the beta function. So what is m comma n here? M is equal to m plus 1 by 2 comma n is equal to n plus 1 by 2. So therefore 1 by 2 will be the same. So beta of the entire integration will be the basic definition in the place of which is in the form of x power m minus 1, 1 minus x power n minus 1 dx. M is equal to m plus 1 by 2, n is equal to n plus 1 by 2. So therefore we can able to write integral 0 to pi by 2 sine power m theta cos power n theta d theta is equal to 1 by 2 beta of m plus 1 by 2 comma n plus 1 by 2. So what is here we are doing? So we are starting with the right hand side. So simply we are taking the substitution and just we are writing the powers, that's all. Okay, so we have to do like this. So next problem, show that integral minus 1 to 1 1 plus x whole power m minus 1 1 minus x whole power n minus 1 dx is equal to 2 power m plus n minus 1 into beta of m comma n. This is one more important property. So they are asking for 5 marks. These three problems we can expect one problem for the university exam. Integral minus 1 to 1 1 plus x whole power m minus 1 1 minus x whole power n minus 1 dx is equal to 2 power m plus n minus 1 beta of m comma n. So we have beta of m comma n is equal to, so integral 0 to 1 x power m minus 1 into 1 minus x power n minus 1 dx. Okay, this is the basic definition of the beta function. So put x is equal to 1 plus y by 2. Put x is equal to, this substitution is very important. So x is equal to 1 plus y by 2. So taking the differentiation on both sides, we have dx is equal to 1 by 2 into dy, and if you could see the limits, when x is equal to 0, that y will become minus 1. When x is equal to 1, that y is equal to 1. So their limits 0 to 1 will become minus 1 to plus 1. So therefore minus 1 to 1 the place of x 1 plus y by 2 whole power m minus 1, 1 minus the place of x 1 plus y by 2 whole power n minus 1, dx is equal to dy by 2. Okay, so now separate the powers, numerator and denominator. 1 plus y power m minus 1 by 2 power m minus 1, 1 minus, so if you take the LCM, that is 2 minus 1 plus y means 1 minus y power n minus 1 by 2 power n minus 1 into 1 by 2. So now in the numerator part we have 1 plus y power m minus 1 and 1 minus y power n minus 1. If we add the denominator powers, because 2 power 1 here, 2 power m minus 1, 2 power n minus 1 here, we combined, put together, that is 2 power m plus n minus 1 minus 1, that is minus 1 we have. This is 2 power plus 1. So minus 2 plus 1 will become minus 1. Clear? Now this is the separate from the integration. So 1 by 2 power m plus n minus 1, integral minus 1 to 1, 1 plus x whole power m minus 1, 1 minus x whole power n minus 1 into dx. So if you see, that is we have to prove. So we are starting with beta of m comma n, and what will you have, that is 1 by 2 power m plus n minus 1. Okay, so if you take this 1 by 2 power m plus n minus 1 into the left hand side, so we have integral minus 1 to 1, 1 plus x whole power m minus 1, 1 minus x whole power n minus 1 dx is equal to, if we take this part into this left side, 2 power m plus n minus 1 into beta of m comma n. So these are some problems in beta function. So in this video we have covered, so what is the beta function, what is the definition of the gamma function, what are the properties of the beta function, what are the properties of the gamma function, and some properties and some standard results on beta function. So we have to show that like this. So we can expect from this part 7 marks, 1 5 marks question and 1 2 marks question. So 2 plus 5 7 marks compulsory we can able to cover from this session. Okay, so and some more properties of the gamma function and the relation between the beta and gamma, and some problems on gamma function we will see in the next lecture. Thank you.